Just as an introduction to the intermolecular forces, I just thought I'd throw this up to show you the intramolecular forces, ionic, covalent, metallic, and just show you just how strong they are. So there's quite an overlap here. We're dealing with intermolecular forces, and there's complexity to that too, because it doesn't just have to be dipole, induced, or hydrogen bonding. You can have all sorts of variations, so maybe a dipole with an induced dipole, or maybe even an ionic. So just an Na or a Cl popping out there attracted to some sort of positive or negative within this. So there's a lot of complexity. We are oversimplifying things a little just to talk about hydrogen bonding, dipole, and London dispersion forces. And you can see that, as you'd expect with the variation of different molecules, there's a lot of overlap here as well with the strength of the bond. So the important thing is when you get a question, most importantly, don't forget to say that London dispersion forces are always present. That may or not be the key part of the answer. And you need to make sure you use the correct IMF terminology and say it's between these particular particles. So let's just go to some examples. So these three here are basically all the same. The only difference is H and F is here, and O and S is here, and N and P is here. So all you're looking at is the strength of the bond based on the electronegativities, and you can see that the ones at the top are far more electronegativity, so they'll be far more polar. So that's the F. That's these first ones here. And so basically once you've done that, because that is, it has to be N, O, or F, this one here is a hydrogen bond. And this one is a hydrogen bond, and this one is a hydrogen bond, funny enough. So these ones are just going to be dipole, so that, and these ones are going to be hydrogen plus its London dispersion forces in all of this here. So that's an easy answer to those. And so these bonds will be stronger, so they'll have higher melting and boiling points. This one is also just another classic one. The OH here is going to cause hydrogen bonding because it's bonded to an oxygen. Whereas this here just has an oxygen in the center, and so it is a dipole, but it is not a hydrogen bonding. So that's a very, very typical answer. It's a very typical question that you're going to get. And this one here is just London dispersion because there's no dipole or hydrogen bonding going on. So this will have the lowest melting boiling point, medium, and the highest melting and boiling points. Just as an addition, it's extremely similar, is the vapor pressure. So the pressure that forms when the vapor of the substance is above the liquid of the substance, and that's based on it having a weak enough intermolecular force to have sort of a very low melting boiling point will make it volatile. So it'll also come off as a vapor very easily. So the molecules with high kinetic energy and weak IMFs will have a higher vapor pressure. And I said to be more volatile. Slightly different, but all to do with IMFs as well as the solubility. So it needs, if it like dissolves like, so if it's like water, which is small and very polar, so the IMFs look very similar to water, it will, look more like water and think it's water and dissolve in water. Whereas if it's very large and non-polar, like wax. Wax is very large molecules, or plastic, very, very large molecules, and non-polar, well, wax is anyway. Some plastics can have polar parts on them, will be insoluble.